So, welcome friends once again to this session of AI Club, and thank you for joining today afternoon. And as I said the last time, this is the last lecture, last theory lecture for this deep learning course, and we'll divide this today's lecture into two parts. One part around half an hour to 40 minutes will concentrate something called transfer learning. After that, we'll give a break of around 5 to 7 minutes, and then we'll have a short session on 15 to 20 minute session on hyperparameters in deep learning. Okay. So I think hyperparameters in deep learning, you have already had some introduction because you guys have applied random search method already in one of the tutorials. So a couple of tutorials you have already solved with automatic hyperparameter tuning in deep learning. So you are aware of that. So we'll not do any hands-on on hyperparameter tuning, but definitely we'll do our hands-on with transfer learning, which someone will take tomorrow. Okay. So with this introduction, we'll start something called transfer learning. So far we have been learning something. A lot of classes we had in deep learning, right? So now I think you guys have already a nice idea of what deep learning is, what is ANN, CNN, RNN, and all that. So you have a nice idea on that. So they were normal neural networks with, let's say, 3-4 kind of layers, 3-4 layers. I think I gave some introduction about VGG16 also, which has lot of there is video on from somebody. I think they put off the video. So okay, so this time we'll go with something called very deep neural networks. Deep neural network means, as you understand, it is who is this? Dr. Shailesh, can you mute your video, please? Yeah. So we will deal with something called very deep neural network. So deep neural network, as you can imagine, like very simple. Like it will have n number of layers, maybe 10, 16, and maybe up to few hundred thousand, a few hundred of layers. So some neural networks have been made by companies like Google, Microsoft, and some startup companies like I'm not getting the name, but they have built up very deep neural network which take months together to train on very sophisticated computers. Okay, so we'll do something related to that. So now, first of all, as we are introducing a new concept today, is called transfer learning. So we'll first get into the term, define the term what is transfer learning. So you see a nice sketch in front of you, and there is task 1 and task 2. Okay, task 1 and task 2, they are written. Upper diagram is task 1, below diagram is task 2. So what we are doing here is, let us first concentrate on task 1. So it's a normal neural network. Task 1 is a normal neural network, which is a very deep neural network with large number of layers. And we are training it with the help of some training data, huge training data. And we are using very sophisticated computers to train this task 1 neural network. Why we are doing so? That once we train this task 1 neural network, we know that previous few layers are for feature extraction, right? And later few layers are fully connected dense layers, which are used for classification or regression. So what we will do in task 2 is we'll use the same neural network, but this time we'll not do the training of this neural network. Training is already done in task 1. Same trained neural network we'll take, and its last layer will change. Suppose task 1 neural network was trained for about 1000 layers, and in task 2 we have only 2 layers. So naturally in our last layer, now last fully connected dense layer, we should have only 10 neurons, right? So previously in task 1, suppose it has 1000 neurons, last layer. Task 2, it is having only 10 neurons. So what we are doing is only last layer we are replacing from 1000 neurons to 10 neurons, our own. Suppose we have 4 neurons, four classes, we'll replace our last layer with neuron with 4 neurons, last layer with 4 neurons. Rest all the layers right from input to in between all the hidden layers will make them untrainable. Will make untrainable. So when we'll train the neural network, which is termed as class 2, all layers are untrainable except the last layer. So what will happen? It is very less, only one layer to be trained, and from last but one layer to last layer, you have some weights. They have to be calculated, weights and biases. So the training will be very quick. So what we have done here is the neural network which was trained in task 1, as it is we have used in task 2. All the layers, and only last layer we have changed from 1000 neuron to say 10 neurons, 10 classes, and we are using it for our purpose. So training has happened somewhere else on the say computers of Microsoft and Google's of the world. They have used very sophisticated computer to train this very deep neural network, and we are downloading those weights and biases in our computer, so local computer, and we are using it to for our own purpose. So training has happened somewhere else, like say US or somewhere else. Training has happened, and we are using that network after downloading. We are using it in our own at our own lab in Bangalore. Okay, so what is happening? Knowledge is getting transferred from task 1 neural network to task 2 neural network. It is a knowledge transfer, right? It is a knowledge transfer, because weights and learning, weights and biases, they only form the overall knowledge. Overall knowledge or overall learning that has happened. In what form training happens in neural network? Training happens in the form of weights and biases. So once you have final weights and biases, means your neural network has learned to do some task. So when training happened of training of neural network happened in task 1, same neural network we have taken in our lab. We have downloaded those weights and biases, changed the last layer to our purpose, and retrained it. So this is something knowledge transfer, right? So this is knowledge transfer, hence the term transfer learning. Training is happening somewhere else, and same neural network we are using in our laboratory. So it is some kind of knowledge transfer is happening. We are not training the full network in our lab, and even if we want to train full network, it is not possible, because those kind of computer systems are simply not available with you. Even with say IIT and all, if you go and you say I want to train this kind of neural network, even I guess those IITs also may not have those kind of computing resources. Okay, so what is the advantage now? Advantage is very big neural network, very deep neural network, which you even couldn't train it in your lab. You are using it to your own advantage. Training has happened somewhere else. You are just downloading weights and biases, removing last layer, retraining it, and then using it to your own advantage. So what is that? Means what you are getting? So that deep neural network you are getting for your own purpose, your own predictions, your own classification problem. You can use it without even fully training the neural network. So your prediction accuracies will be very, very accurate, because that deep neural network is very, like, it contains a lot of layers, neurons, weights and biases. It was very accurately trained for doing some kind of classification task. Same kind of accuracy you can get with the help of that neural network if you are using it at your lab. And mind it, with the transfer learning, accuracy is more than 95% are possible. Like if you train your own neural network from scratch, so maybe that you will get accuracy up to 85-90%. Very difficult beyond that. But with transfer learning kind of system, you can get accuracies even beyond 95%. So now we one of the very famous and classical very deep neural network is called VGG16. So VGG16 is a standard neural network nowadays for classification purpose. Even if you are doing a classification problem with 4 class, 10 class, 6 class, 8 class, whatever you have, you can use this VGG16 for your purpose. So originally it was designed for visual recognition. So it has 1000 categories. 1000 categories it has, 1000 classes it had when it was trained originally. 1000 classes, and each class had 1000 images. So total number of images on which this VG16 was trained was 1.2 million training images it was trained on. And it was trained for a classification type of problem. And that classification type of problem had 1000 classes. So last layer was having 1000 neurons. So if you see the structure of this VG16, you can see that convolution layer, then max pooling layers, and then fully connected layers. So, and input images on the very extreme left hand side. So from this diagram, it is little difficult to imagine this network. You see a simpler diagram which you can understand VG16. There is an input layer, then 2 convolution layer, then pooling layer, then again 2 convolution, 1 pooling, then 3 convolution, 1 pooling, 3 convolution, 1 pooling, then 3 convolution, 1 pooling. Like that you have, then after that you have a set of, last you have a set of 3 dense layers. And that the last layer is doing the class of classification job, and that last layer is having 1000 neurons. Now if you want the dimensions of these neurons they are given here, like 224 into 224 into 64. Like you can read it like input 224 by 224 by 64. So you have to read in a standard CNN way. So CNN, whatever CNN layers are there, their in the dimensions are given here. So you can first is bigger CNN layer, then size is getting reduced, and reduced. Okay, so this we are not much concerned with the structure of this, because rarely we are going to train it on our own fully. We'll never train it. What we'll do is we'll simply remove the last dense layer. It has used 1000 classes. We'll use with our, suppose we have 8 classes in our classification problem. Last dense layer will replace from 1000 to 8 neurons, and then regauge the weights between the pooling layer and the dense layers. So I'll take you how it is done. Like first, initially, like if you want to use it VG16 for your own problem, initially what you do, like only the last layer you remove. And from last layer it had 1000 neuron. You put your own classes. Suppose you had 8 classes, you put 8 neurons there and train it. Some kind of accuracy you will get. Okay, then maybe, and rest all layers are frozen layers. Frozen layer means their weights and biases are frozen. Whatever it has come trained from the original company, we are not changing them. So they are frozen layers. So next step you can do, what you can do is, instead of training only 1 layer, you can train 2 dense layers. So you see here VG16 is having 3 dense layers. So you can train, instead of freezing the like 2 dense layer, you just open them also for training. So now all the dense layers, dense layer 1, dense layer 2, and dense layer 3, all the 3 training layers, you can keep it open for training. Rest everything you can freeze. So like that in 2 stages you do. First stage, you keep last layer only. Last layer you just change the last layer, keep everything, freeze, including the 2 dense layer, you freeze them, no change. Then you, in this next stage, you can open 2 dense layer or 3 dense layer for training, and rest everything can be freezed. Like that you can use it. And believe me, like if you do this kind of training, within 10 to 15 minutes, your neural network training is over. And if you recall our CNN lessons, so input is the dog here, and in between whatever convolution and pooling layers you have. So they are nothing but they are feature extractors, right? They are feature extractors. They are extracting features for you. Features of what? Features of that image. Okay. So image is having a very large number of features. Every pixel is a feature. So now after that you are applying pooling, then you are applying convolution, then pooling, then convolution, then pooling. So different levels of features you are extracting. And final feature set, whatever you are getting in the final pooling layer, that you are passing in the dense layer for classification. That's how CNN was, right? So VGG16 also no different. It is same. So, but you have multiple sets of convolution and pooling. So I think if I'm not wrong, this particular network was trained by Oxford University. I'm not 100% sure, but mostly like if you web it, Google it, you'll find that it was mostly like 99% it was trained by Oxford University. We use it, and then as I said, you can use it for your own advantage. First, change the last layer. 1000 classes it is having an original. You put your own number of classes, 6, 10, 6 at 10, whatever are there in your problem, and keep 2 dense layer frozen. Don't change their weights. And in next step, you keep 2 dense layer open for training, or 3 dense layer open for training. So that will be very clear how to freeze the layer, how to open the layer for training. So that when someone will take theory, we'll take a hands-on class tomorrow, so those things will be very clear. So it is possible for you to freeze the number of layers you want, and it is possible for you to open the number of layers for training. So suppose if you want last convolution, you want to train last convolution block also. So you can keep, there are 4 convolution blocks, right? So these 4 convolution blocks you can freeze, and the last convolution block with 3 convolution and 1 pooling layer, that you can open for training. So it depends on the accuracy you are getting. So if you are not satisfied with training only the dense layers, you can open this convolution block also for training. That is also possible. So you can train only that much area, like 3 convolution block, 3 convolution layer, 1 pooling, and 3 dense layers. This much you can train at your own lab or your own computing. So those kind of arrangements are possible, and then you can use it for your own purpose. And now VGG16 is one of the de facto classifier problem. Like I think many companies, many startups, or many companies with less computing resources, they don't want you to use this kind of transfer learning. They don't want to use something called VGG16 and all that. They are telling that you could develop complete neural network from scratch. There are some reason for those companies to do that. But most of the companies you go, they will allow you to use networks like VGG16 and all. So by opening the number of layers, like as I said, you can open either 2 dense layers, or you can over a convolution block pooling. You can train it specific to your own problem. Okay, so this is a first very simple concept, and I explained you why it is called transfer learning, because knowledge transfer is happening. Weights and biases, weights and biases that we are getting are trained. We are trained at somewhere else in Oxford, and we are using it for our own purpose without even changing it. Only 1 or 2 layers we are opening for training. So it is transfer learning. Knowledge transfer is happening. This is one of the things. So VG16 is one of the de facto, like very famous kind of, or very standard network which people use for classification purpose. You can also use it. Okay. Now what happens? I will give you some advantages or disadvantages of VG16. So VG16 does in classification fairly good accuracy you can get. Okay, and you can use it for most like whatever image you have for classification. You can use for most any kind of architecture. Like if you want to classify houses, you want to classify animals, you want to classify cars, you want to classify trucks, aeroplanes, whatever architecture you have, in the image type of images you have, you can jolly well use VGG16. And one advantage is that you can get a fairly good amount of accuracy with the help of it. But disadvantages are also related with that. It is painfully slow to train. It takes a lot of time to train. And VG16 size is very huge. So VG16 bits original VG16 when you download with original weights and biases, it is 533. It comes original weights and biases when you download original VG16 without any change, then it is 533 MB. 533 MB it is original total model size. Model size is 533 MB, which is used. So deploying a VG16 is a tiresome task in a small devices and embedded devices like mobile and all. It is not possible to deploy this kind of model. So transfer learning is used in mobiles also. Nowadays, mobiles also use transfer learning, but they have specific models developed for mobile phones, mobile operating systems, the kind of computing resources which you have in mobile phone. For those kind of situation scenarios also, you have some transfer learning models available. So one of them I can name is called MobileNet. The name itself you can tell that it is used in mobiles, MobileNet. But VG16 is very huge, so you cannot deploy it in smaller machines. And training it is a very painful task. It trains very slow. But if you have a fairly good amount of say resources like Google Colab Pro and all available, jolly well you can use it, and in a reasonable time you can get your 2-3 dense layer, whatever you wanted to train, you can train in reasonable time, and whatever resulting model is there, you can use it for production. Okay, and there is no copyright on this. You can use it for your own purpose, commercial purpose, production purpose, you can use it. So I take a minute break here, and I just open it for questions for a minute break I am taking. So Shrutika madam, any questions? So this is one architecture we have understood. Yeah, madam, go ahead.
No, sir. No questions as of now.
Dr. Shailesh Shoman.
I'm not sure.
Dr. Shailesh?
Yeah, one question is, am I audible?
Yeah, audible. You are audible.
For this, already my output and input are means output layer is different. So how this means already this derivative with respect to alpha, sorry, bias and weights are considered, and then
see it is VG16 as I told you here in this slide. If you can see, it has been trained on 1.2 million training images. 1.2 million training images has been trained. Okay. And 1000 classes, it has been trained on 1000 classes. Each 1000 was having 1000 images. Each class was having 1000 images. So why I am telling this is that training something with 1.2 million images is a fairly general, so this is a very fairly general kind of classification. So the weights and biases are adjusted to general classification. Like it is 1.2 million means it is almost covering a lot of possible cases which you are going to use in your problems.
Okay, so what we are saying is since for 1000 classification itself, those weights and biases are defined.
Yeah.
So if I have only 8 classes,
yeah, 8 classes, it should work. And suppose, yeah, go ahead.
So all the existing calculation weights and biases, which are calculated for 1000, so obviously that will work for smaller problems.
Yeah, so that is what is the idea. Yeah. Okay. And see, I am telling you, there are different schemes, like different schemes. I told you first you open only one dense layer for training. You see the accuracy results. If you are not okay, you open 2 dense layer, then you open 3 dense layer. If you are not okay with the results, you open 3 convolution, this last convolution block, 3 convolution and 1 pooling, and all the 3 dense layer. So similarly, you can keep on opening more and more layers of this VG16 for training, and you can match it, you can train it to match your problem. Understood, no?
Okay. Yeah, I got it.
Yeah, and I have seen some, you see, if my memory is correct, I have seen some problems in which VG16 is trained, totally they have trained it. Like they have taken the architecture as it is. See, same architecture they have taken, this architecture. Architecture they have not changed. But all the layers for all the convolution, pooling and dense layer, they have opened for training. People have done that also. You can also do that. Very simple. Just open them for training. Model will take more time to train, but it will train to a specific problem. And if your VG16 is not working out for you, use VGG19. And there are a lot of other available, like Google Net is available. Resnet is Google Net is from Google, and Resnet is from Microsoft. Those kind of also available for classification. You try them, one of them. You try them. Multiple you can try. So it is not a category. It is not. I'm not telling that one VG16 will suit for all the classification type problem in the world. Man, no, it is not the case. You try first. If you are not happy, try training more layers. If you are not happy, go with some other. No, VGG19 accuracy is better than VGG16. So go for VGG19. Go for ResNet. Go for even mobile net. You can use mobile net. You can. It's not necessary that it should be used only in mobiles. You can use it. You can use ResNet. You can use Google Net. You can use. So many other are available. Yeah, at least 50 to 52 I have seen. I have made one document in last March 2020 March. I made one document in which I have listed pros and cons of 52 such model transfer learning models. VG16 is only one of them. I have listed around 52 models like that. So I'll share that document with you. Okay, I have to search a bit.
Okay. So all these are publicly available and
Publicly available, yeah.
proprietary, no copyright, everything
You
is
just
open.
Google it out, download VG16, you will get it.
Oh,
And then find some tutorial how to use it. In the similar way, you use it for your own. And anyway, someone will take a class on class tomorrow, so you will understand how to use it. Using it damn simple. Using it, coding is very simple for this. Now, next, I want to explain you architectures. So this is one of the architectures, one of the simple architectures in which transfer learning was made available, and it is one of the very standard. VG16 is one of the standard neural network to transfer learning model for you to. So you should try this. Okay, not, but as you, what happens is there are number of layers or more, right? So I think in multiple occasions in our previous classes I have explained to you, like the number of layers, if they decrease, so they face some kind of problem called, if your neural network becomes deeper and deeper, you face some kind of problem called vanishing gradient and exploding gradient. I think we have done this in RNN also. We have done exploding gradient. So we were facing the problem of vanishing gradient and exploding gradient. That's why we are not using plain RNN. We are going for LSTM or GRU, right? So that's where we introduced vanishing gradients. So same problem is here also. Vanishing gradient is what in back propagation. All your weights and biases are updated using the partial derivative of your loss function, right? So what happens as you go backward, that partial derivative of loss function become very close to zero. So what will happen? Training will not happen. Na? Your weights and biases will not change because they are changed using that partial derivative only. So that partial derivative of the loss function becomes very, like as you start from loss dense layer towards the first input layer, somewhere in between the partial derivative will become near to zero. Very minor, very small. So training will not happen. So that is called vanishing gradient. So to solve that vanishing gradient, they have come up with one more architecture, which is called, which is the innovative architecture which Resnet has developed. So like they want deeper and deeper neural networks. Why they want? Because it gives them better and better accuracy. More deeper neural network goes, it can accuracy can increase and it can solve more variety of problems. So the aim of the race, researcher want more. Somebody has developed with 400 layers. Next group of researcher will want to develop with 1000 layers. So that is a race, kind of race going in research field, or in researcher there is a race to become who builds up a deeper neural network successfully. So there are obvious advantages of building neural network more deep and deep. So there are advantages. But what happens, as we said, as they become deeper and deeper from last layer towards the first layer, somewhere in between your partial derivative of loss function will become very close to zero, and updation of weights and biases will not take place. So training will not happen. So this problem was faced by a lot of researchers, and they were not able to get past this problem. They are not able to rectify this problem. So this Resnet and some other people, they have come up with an innovative architecture. See, you see here in this diagram, layer 1, 2, layer 1, L1, L2, layer 1, layer L1, and layer L2. There are these layers are there, right? So L1 is your maybe say assume that layer 1 is output layer, and then after that you have hidden layers. So what is happening from layer 1, layer L2 to layer 1? There is a direct connection. There is a direct connection. So this is nothing but your short circuit here. Your electrical short circuit, you know, no? So simple, someone can explain that what is a short circuit. So suppose there is a resistance in between in there are 2 points in the circuit, and in between there is a very big resistance, say of 1000 ohms. There is a resistance of 1000 ohms. So if you have to pass that resistance, what you will do, Soman? If you don't want to, you want to pass that resistor, what you will do?
You just short circuit that point.
Yeah, you have to short circuit 2 points. So direct
across the end.
Yeah, you just connect point 1 and point 2 are currently connected by a resistor. If you don't want to use it, just connect wire and wire 2 directly. That's how you can bypass resistance, right? So this is the analogy I want to take here. So what they do is, suppose layer up to layer L2, there is some accuracy or performance of the neural network. I have introduced one more layer in between, which is L1. And if I see by introducing the layer L1, my performance is deteriorating. My performance, suppose in L2 level, I was getting accuracy of 92%. After adding layer, I am getting accuracy of only 90%. Then why I want layer L1? I don't want layer L1. So whatever layer output is coming from layer L2, I'll use the same. So same is the concept here, which is called residual blocks. So residual block means, suppose the performance of middle layer is not good. So I take input directly from the previous layers. So I'm short circuiting it. I'm shunting it. So this is what. So what is the advantage? So the performance of neural network by adding a layer L1, and at the layer 1, either you will get better performance because of L1, or you will get performance which is as good as L2. That is ensured, right? That is ensured. Because at L1, you will never get a performance which is less than L2. Because why? Because you are having a short circuit here. If L1 is not performing, I just bypass it. I won't use it. Just bypass it means I'll use its weights and biases 0. Connection 0. My layer L2 will directly connect it to layer 1. My layer L2 will directly connect it to layer 1, because in between layer is not performing. So on the same principle, I think it was done by Microsoft, and it is a very innovative architecture in deep learning. And with this, because of this architecture, very, very, very deep learning neural networks are possible. They are going on adding blocks of convolution blocks and blocks of blocks. If some part is not performing well, just bypass it. So this is the architecture which they have come up with, Resnet 18 architecture. See, then you see carefully, you see it a little bit carefully. There is a first convolution block, then pooling block, 3 by 3 pooling block, and then there is a convolution block in between. Like 3 by 3, 64, same convolution block. but there is a shunting also is there. There is a bypass also is going on. So there are very lot of bypass connections here. There are a lot of skip connections here. So that means any of these blocks, if it doesn't perform properly, directly I'll jump at that block and I'll go next. So this was one of the very innovative architecture, very simple idea, but in neural network it is considered as one of the very landmark innovation and landmark performance. So with this kind of innovation, more deeper neural networks are possible. And what it is doing, it is solving the problem of vanishing gradient, which I explained to you. Vanishing gradient problem is getting solved. So I'll read the last bullet. It means the higher layer will perform at least as good as the lower layer and not worse. I told you, na, here at layer 1, if I get performance at least which was there up to layer 2. If layer 1 is not performing, at least up to layer 2 I'll get performance in layer L1. And if layer 1 is giving good performance, I'll not use this bypass. I will use layer 1 also. So at least that is ensured. Simple concept. And that Resnet is again available as your transfer learning model. So you can same concept here also. You can open say 3-4 layer, whatever layer you want to open for training, you can open. Rest everything can be frozen. They will not be trained. They will not be trained means their weights and biases will be as same as they are coming from the original Microsoft training. They will not be changed. And it is up to you how many layers you want to keep for, how many layers you keep for training, open for training. So it is up to you. So based on your application, you can use it. So what is the advantage? It is solving the problem of vanishing gradients. And with this arrangement, very deep neural networks are possible. So see here, these graphs in the below side, bottommost side of the right hand side, bottommost graphs you see. Like one plain neural network is there. See the validation curve is deviating. Training curve is coming down, which is green one. So validation, like in validation, loss is going up. Up till one point, it is coming. It is coming very close to training, and after that, it is diverging. And if you use Resnet, it comes uniformly. So advantage of the Resnet is definitely there. This kind of stiff connections are offering us more advantage, because we are both in validation and training. We are going to get reduce the losses. We are getting better accuracy with the help of this kind of skip connections. So these are two basic architectures which we have to remember in transfer learning. And I think now in TensorFlow or PyTorch, somewhere in TensorFlow also, you can this kind of residual blocks you see, residual blocks. So this kind of block itself are adding those blocks is possible. Like you need not add this convolution pooling separately. One residual block is as it is. You can use pickup from. It is just pick up from the TensorFlow, one of them, and you can use it. So you know that Lego or these blocks. No, some blocks are just blocks are available. Add it. So some these kind of residual blocks are ready-made also available in TensorFlow and PyTorch, which you can ready-made use it. So it makes your life easy. So this kind of you can make your own neural network architecture, and so these are two definite architectures and concept of neural network which want to be a transfer learning, which I wanted to discuss with you. So these are some inception net, exception net, VGG, Resnet. So different statistics is given. So number of parameters in inception net is 23.62 million. Exception net 22.85. VGG you see lot of parameters, 138 million trainable parameters, and Resnet is having 23 million parameters. But complexity of complexity of, in this 4 type of transfer learning, you just see the complexity of VGG is very high. VGG is very high and speed is low. VGG, complexity is very high and speed is very low. So it is one of the earlier architectures like VGG16 when transfer learning concept was new. So that time this kind of VGG16 was introduced. So it is older architecture. So you can use now better ones like you can use Resnet, you can use Inception Net, you can use Exception Net. So you see their complexity also low and speed is also high. Even better ones are available. Google Net is not given here. So you see the same for some data is given. So you see the Exception Net top 1 accuracy 0.79 and top 5 accuracy is 0.945. So I'll explain you what is top 1 accuracy. So sometime back, I think we have discussed something called multi-label classification and multi-class classification. Multi-class classification means you have multiple classes in that, but at a time only one class has to be predicted. One class will be true. Multi-label classification means there is something in a plate of in your food plate you have, and there are different type of food plates having different items. So in that food plate, suppose each food plate is having only 3 type of item, different item, but only 3 type of item. So whenever you will do a prediction, you will predict for 3 items. That plate number 1 has level 1, level 2, level 3, 3 kind, and then dish 2 has level 5, level 3, and level 6. So multiple predictions will be there. That is called multi-level classification, and multi-class classification will be only one. Only one will be there. There are multiple classes in your problem, but at a time only one will be true. So top 5 accuracy means it is a multi-level problem. At a time 5 classes have to be predicted in top 5 accuracy. 5 labels are there which are to be predicted. So that is a standard way of looking at it. So you are it is a top 5 accuracy means your problem it is a multi-label classification and it is having 5 classes to be predicted at a time. So in multi-level top 5 accuracy and top 1 accuracy, you can compare these results actually with some kind of standard database. With some standard database, I think you can compare the results of different. So Exception Net is giving the best results. VGG is giving lowest results. And Inception Net also very close to it. Resnet 0.933 and Inception Net and Exception Net are very close. You see, one is in top 1 accuracy also and top 5 accuracy also. So I'll take a minute break here and I will just want to ask this basic question here. Is there any problem have you understood what is top 1 accuracy, top 5 accuracy? Dr. Shailesh? Have you understood what is top 1 accuracy, what is top 5 accuracy? Are you able to hear me, Dr. Shailesh?
Yeah.
So have you understood what is top 1 accuracy, what is top 5 accuracy?
Right. So basically, top 5 is having better accuracy than top 1. Yeah,
top 5 is a multi-label classification. At a time, out of suppose your 20 classes are there, in which at a time you are predicting 5 classes. Out of 20, that 5 may be true.
Right.
So that is multi-level. And suppose here in top 1 accuracy means you are having 20 classes, but at a time only one will be true.
Yes.
So that is difference between top 1, top 5. So top 1 is a multi-class classification and top 5 is a multi-level classification. There is a difference in both. I think multiple times we have discussed. And I think with this, I finished the transfer learning. And concept is very simple. And after that, Soman will take, tomorrow Soman will take its hands-on. Very simple coding. No, it's absolutely no results. And once you learn how to use transfer learning with VGG, you can use any of these models. little bit there will be a readme page of this. Every model will have its readme page documentation. Just 5-10 minutes it will go through documentation, and the same way you are using VGG, you can use any transfer learning model, whether it is Inception, Exception, Resnet, VGG, or Google Net, whatever. You can, in the same way you have to use. Little bit documentation you have to use or read about it to know more familiarity, to increase the familiarity. Same way you can use it. Mobile net is there. There are so many. So you need not learn everything separately, each and every model separately, but you should know when to use what kind of transfer learning model. So that I'm not covering in today's session, that in which situation you have to use what kind of transfer learning model. For that, I will give you a document to you, which you can read. I prepared in 2020 March, I prepared that document. Around 52 model transfer learning models I had included, and each pros and cons and when to use what I have included there. So that I cannot discuss in this class like this, in a 1 hour class like this. I'll give you that model document and you can have use it as a reference. So that's end of transfer learning theory class. And now we'll give now we'll break for 5 minutes, and then we'll gather again for hyperparameter tuning, which is again 20 minutes lecture. So